What's going on, everybody? Jake here, coming at you with another live math lesson this Monday night. It's Monday, September 12th, 2022, and coming at you with my weekly live stream. Sorry I'm doing it just a few minutes late today, but still got some good stuff for you planned. We're going to be getting in a bit more into kind of on the topic of limits that we talked about last week. We're going to build on that a bit and talk a bit about continuity and discontinuity. So we're going to be going over a couple different examples here, which are examples that you're likely to run into in a calculus class when talking about intervals of concavity and discontinuities within a function. Specifically, we're going to be talking a bit about from kind of the graphing side what these things look like. So I have a couple examples here, which in one of them you're given a graph and you have to kind of talk about continuous intervals and discontinuities within that graph. And then we're going to be talking a bit about what it looks like to kind of go the other way, where basically you're given information about where a function's continuous or discontinuous, and we have to graph it. So a couple helpful things we're going to be talking about today. As always with these live streams, if you do have questions along the way, just throw them in the live chat. Even if they're off topic, I'm happy to help answer any questions I can while we're here, while we're talking about this stuff live. So let's go ahead and jump into the first problem here, and I'll get into some of this stuff. So we're going to start out with this one here. From the graph of G, state the intervals on which G is continuous. So obviously we are given a graph of our function. This basically blue lines are our function G. So you can see in this case it's graphed on the XY axis, and we have this function that's been graphed to us. So we have to figure out which intervals is G continuous, and I guess I should say a part of doing that is finding discontinuities. I know the problem doesn't specifically state for us to, state the discontinuities, but that's obviously a helpful piece in doing this. So when you look at a graph of a function like this, obviously this is, fairly complex piecewise function. We have several different pieces that are all, separated. Our graph has different representations on these different intervals, and we have to kind of figure out where it's continuous and where it's not. So how do you do something like that? Well, the kind of simplest way I like to think of what it looks like for a graph of a function to be continuous is, can you draw your graph without lifting your pencil or your pen off the paper? So essentially, what parts of this function, if we were to basically just imagine starting from left to right, so we're just going to basically start on the left here and go this direction. As we go from left to right, what parts of this function can we draw without ever picking up our pen? Well, you can see we're going to start here at x equals -4, and we can draw all the way up until -2. So right here, let me actually kind of trace along the function. We can start at x equals -4 and move along our blue line here, and we would not have to pick up our pencil until we get to x equals -2. So right here, at x equals -2 is the first point where we have to pick up our pen to then draw the next point on our graph. So you can see, if you imagine kind of a vertical line at x equals -2, the y value, or the output, or the height of our piecewise function changes at that point, and changes in a more kind of drastic way that it wasn't before, right? All throughout this period of time, obviously the output, the y value, is changing, but it was kind of a slow process, right? And we could draw that whole section without picking up our pen because there was no point where we just like jumped from one height to another. We kind of slowly went from this height here down to this height here in a nice continuous line. So graphically what that looks like is just a solid line with no holes, no jumps, no asymptotes. There's obviously a handful of different things that can cause a point or a section of discontinuity, but what that really doesn't look like is a continuous, I'm trying not to use the word continuous to describe continuous, but it really is the best way to kind of think about it, is a line with no breaks in it, essentially, is all that comes down to. So then we have our first break, our first jump from right here down to right here. And then this is just one point. It's not a line. To continue right along our function, we then would have to jump again further way down to here. So this is basically a point of discontinuity, because we have to pick up our pen here, draw a point here, pick up our pen again, and then continue drawing our function over here. So we basically have to pick up our pen twice just at this one x value to draw our function. Then continuing down here, we can keep on drawing this whole section here. We got a nice solid blue line taking us all the way to x equals 2 without ever picking up our pen. And then again, at x equals 2, we have to pick up our pen and put it way down here to continue drawing our function. So basically we have a discontinuity at x equals -2, at x equals 2. And then we continue drawing off to the right here. And I know right here it's maybe not super clear what's going on. What this does look like, though, is that we have a vertical asymptote right here at x equals 4. And again, I know it's not explicitly stated in this graph here, but you can see basically from both the left and the right, our function is just approaching that kind of gap in a way that looks like they would just kind of continue on at a vertical asymptote right here up to infinity. So I think it's safe to assume we have a vertical asymptote right here. So what that vertical asymptote means is at x equals 4 exactly, at that x value, there's not going to be a point where kind of this chunk of our graph here connects with this chunk of our graph here. So again, we can say we have another discontinuity at x equals 4. Then we continue drawing our function along to the right here, and again, get to a point where we have a hole, a point, and a hole. So we have to jump from down here up to here, draw this point, and then jump all the way up to here again in order to continue drawing. So basically we have another discontinuity at x equals 6. And then we can continue drawing all the way to x equals 8, where our function just kind of ends, basically. So x equals 8 is the next kind of end of our continuity, and basically the end of the domain of our function. So now we have to actually think about the intervals where this was continuous. Obviously, what we've done here is we've basically listed out a handful of different points where our function is discontinuities. But from that, we need to gather intervals of continuity, intervals where our function is continuous. So to do that, what we really want to think about is basically how this is going to be listed out, or what our answer is actually going to look like. We need to basically draw this out in intervals. So what an interval means is x values between specific numbers. There's kind of two different ways you can actually write that out, and I'll talk about both of those. So basically we were continuous all the way from x equals -4 to x equals 2. So we know between x equals -4 and x equals -2, our function is continuous. So this would be one interval of continuity. However, what we also need to consider is our endpoints. So we have, obviously we know that -4 and -2 are the endpoints of this interval. It's continuous for everywhere between there because we could connect them without picking up our pen. But what about at x equals -4 and at x equals -2? Specifically, from this little section right in here. So at x equals -4 from the right and at x equals -2 from the left, is it continuous or discontinuous? So for x equals -4 from the right, since we can get all the way to x equals -4, this was a solid dot, which means that x equals -4 is actually included in the end of this little line segment right here. What that means is, as we approach x equals -4 from the right, all the way up into and through x equals -4, this is continuous. So this should actually be x greater than or equal to -4, because it's continuous all the way into -4 from the right specifically. So that's something to kind of keep in mind here. We're looking at places from the right. So actually, I guess you'd want to be a little bit careful there, because this problem is saying intervals where our function is continuous. That actually, that kind of implies that we're talking about two-sided continuity. Is it continuous from both sides? So actually, we probably would not want to include x equals -4 in that, because it would be continuous from the right at x equals -4, but not from the left, because we don't have anything kind of connecting into that point. So it probably would be safe to say that this point is not continuous there, which is kind of what this problem is getting at, two-way continuity. So then over here, if it were specifically mentioning one-way continuity as well, we could say that it was continuous from the right at x equals 4. But since it's not continuous from the left, let's kind of ignore it from our intervals of continuity here. So then at x equals 2, we have this jump here, so it's not continuous at x equals -2. We can't include -2 in there because of that jump and then that other jump again. So then starting at x equals -2 and going on to the right there, it's continuous because we can continue to draw our function without ever picking up our pen all the way until we get to x equals 2. So then to x equals 2, and then from 2 up to 4, same kind of pattern continues. And then from 4 on to 6. And then from 6 on to 8. So this is, whoops. So this is one way that that we can actually write out these intervals, would be to kind of write it like this. There's another, I don't know what you'd call it, a notation, I guess, another kind of format, a way to write these intervals, which would be using brackets and parentheses. So to do that, all you have to do is look at your endpoints of your greater than and less thans that we wrote up here. And if it is greater than or equal to, you would use a square bracket. If it was just greater than, we would use a round parenthesis. So this case, we have x greater than -4, so we'd use a round parenthesis. First, we would write the -4, so the left endpoint of our interval, then a comma, and then the right endpoint of our interval. And then since this is x less than -2, not less than or equal to, we would use a round parenthesis. So this would be the same as this interval right here. Okay. Then we can basically just do the same thing for all these. And then what we would put in between them is a union. So the kind of U symbol basically means the union of these two intervals. So our function is continuous on this interval, as well as this interval, as well as this interval, as well as this interval, and this one. So either of these, depending on the context, is probably an okay answer. Typically, I would recommend going with this second one. The kind of parenthesis and bracket approach is generally going to be the better way to write this answer. So this would probably be our ideal answer right here. So if you are getting some value out of this so far, do me a huge favor and hit that like button down below. Helps really get these videos out to more and more people so we can keep growing the Jake's Math Lessons community and keep crushing it all term long in calculus together. So let's go ahead and move on to this next problem here. Here we're going to basically reverse engineer the last problem that we did. So the problem we have is sketch the graph of a function f that is continuous except for the stated discontinuity. So in this case, the discontinuity stated is we have discontinuities at -1 and 4, but continuous from the left at -1 and from the right at 4. So what we have to do is kind of sort through the information we're given here. We know that our function is going to be continuous everywhere except for at two specific points in this case. We know we have discontinuities at x equals -1 and x equals 4. So those are going to be really the only two places where our function is going to be discontinuous. So what we can start with is just drawing out our xy axis first of all. Okay, so the other thing to kind of keep in mind with problems like this, there are obviously several different graphs that would satisfy these requirements. So anything that does meet these requirements would be fine. So there are, kind of multiple different answers of what your graph could look like, as long as it satisfies these couple of things. So let's go ahead and label our x-axis here. Kind of like the last example we talked about. It's okay if we don't really label our y-axis, because this doesn't have any requirements about how high our function should be up and down the y-axis. It just has requirements about what x values have discontinuities. So if we label this, it's fine that our y-axis is not labeled. Okay, so what I like to do is just kind of list out what we know about specific x values. So we know x equals -1 and x equals 4 are the only places where something a little bit weird is happening. Other than that, it's going to be continuous everywhere else. So if we look at these 2 points, what do we know about what our function needs to look like at x equals -1 and at x equals 4? We know obviously that it's going to have a discontinuity, but we have even more specific information than that. We know it needs to be continuous from the left at x equals 1. So continuous from the left, and from the right at x equals 4. So CTS is just the abbreviation for continuous. So continuous from the right at x equals 4. So continuous everywhere else other than that. So really, x equals -1, so right here, and x equals 4 are the 2 places that we want to kind of focus on. So we need something that is continuous from the left at x equals -1. So what would that look like? If we know that our function needs to be continuous from the left at x equals -1, that means we're going to have a basically, we need the point at x equals -1 to connect with our function going off to the left from there. So we know that whatever we do with our function over here, it has to basically end right here with a solid dot. We need this point to be included in this line segment. Basically what that tells us, or what that eliminates, is there's a few things that we can't do with our function at that point, which would be if we had like an open circle and our function going off to the left like that. That would not be continuous from the left at x equals -1. Or if we put a vertical asymptote at x equals -1 and our function going to that vertical asymptote infinitely up or infinitely down, this would not be continuous at x equals -1 from the left. So it does eliminate a couple of things for us, but what it does tell us is that as long as we have a solid dot here and then our function goes off to the left from there, we should be good, because it should be still continuous from the left at that point. Now, what we need to make sure happens to the right of x equals -1 is that our function is discontinuous there. So we can't continue on our function from the right at that point, right? It can't connect to that, because if we do, then our function is fully continuous at x equals -1, and we don't have a discontinuity at that point like we need. So that's what we can't do. What we can do is really anything else. We can either put an open point right there and have our function continue off to the right from there. We could have maybe a vertical asymptote at that point going off to the right, going infinitely down or infinitely up at that point, as long as we made sure it was continuous from the left. So we do have options. It's really up to kind of whatever one you want to do. Both of those things that I just mentioned would be right. So if you like one of those or the other, pick it. Speaking of liking, if you are liking this video, do me a favor and hit that like button down below, please. Huge help to my channel. And if you are getting some value out of this video, I would greatly appreciate the like. So go hit that thumbs up button. So let's just go ahead, and I'm going to go with the open circle approach. So we'll just put an open circle, and then our function is going to go off to the right from there. Okay, so this kind of a scenario right here, what we've just kind of drawn at x equals -1, takes care of everything we needed at x equals -1. Okay, so similarly, we need to do the same kind of thing at x equals 4. We need to make sure it's continuous from the right, though, instead of from the left. So kind of like over here, how we had to have the solid dot with the line going off to the left. Over here, we have to have the solid dot with the line going off to the right because it needs to be continuous from the right. Then from the left, it needs to be discontinuous. So we cannot connect that there because then that's continuous at that point. However, what we can do is make, let's say, a vertical asymptote this time from the left only, as long as you don't have this asymptote, affecting what's going on to the right. So basically we can say that we have a vertical asymptote going up to infinity from the left, but then from the right, we have a solid dot at this point and it carries on to the right. So other than these kind of two sections doing what I've drawn here, we can kind of connect the rest however we want. We do have to make sure it's a function, so it needs to be able to pass the vertical line test. But other than that, it's kind of up to you how you want to do it. We do know it needs to be continuous, so we can't have any other discontinuities anywhere over here, anywhere in between these 2 points, -1 to 4, or anywhere over here off to positive infinity. It does need to be continuous. So that means this function does need to continue on infinitely to the positive x direction and the positive or negative x direction. But what it does before that, it's kind of up to you, whatever you feel like. So we could do something squiggly over here. We could do kind of sharp corners in between here. Really does not matter. We could just be boring and just make 3 straight lines. Really does not matter. But this would be a perfectly good example of a function that has discontinuities at x equals -1 and 4, but is still continuous from the left at -1, continuous from the right at 4, and continuous everywhere else on the entire domain besides x equals -1 and 4. So that meets the requirements of what this problem asks us to do. So again, if you did get some value out of this video, please hit that like button and subscribe down below as well. Turn that bell icon on so you're notified when my new videos come out, and we'll keep crushing it all term long together and get your calculus grade up to where you want it. I do these weekly live streams every Monday night at 5 o'clock Pacific time. I know I did start a little bit late tonight, but usually they're at 5 Pacific time. So be sure to subscribe and come back next week and join me then. And if you want to keep learning about continuity, I have made several other videos on that. Just go check out my channel and keep this brain train rolling. Thanks, and see you next time.